Hi, everybody. Today, we shall demonstrate with you how we can carry out regression when we have more than one feature or independent variable. In real situations, the target depends on more than one feature, and usually feature analysis is done before regression so that we can decide what are the most influential and most important features which should be taken in consideration and used within the regression process. So multiple regression means that there are more than one feature or independent variable which must be considered by the regressor. These features, as a result of what I have said, must be considered when writing the expression of the regression function, and they appear as terms of that variable multiplied by a coefficient which gives its weight. The regression process ends with giving values, the best and optimum values of the coefficients which are multiplied by these features. In addition of knowing these coefficients, of course, we can, as usually, carry out some tests to decide the quality of regression, the accuracy of the regressor. This is important. And also it is important to draw the curve which represents predicted values relative to the original scatter plot which we have with the original data. So let us begin our work with this simple example here, where we shall use curve fit, where we shall use, curve fit function of Scipy, and try to plot the dependency between two independent variables and the target. So at the beginning, we import the necessary libraries as usual. Then we define the model. In this example, I am working with a nonlinear model function. So the function will not be a straight line. It will be somehow curved. And according to that, the expression of the nonlinear model will depend on some coefficients. Here we are taking three coefficients, C1, C2, and C3, and the independent variables which are represented as a two-dimensional array here, X. So X here includes two variables, X1 and X2. X of 0 is X1, and x of 1 is x2. Now we use x1 and x2 in our model function. It is nonlinear. We are using an exponential function multiplied by the first coefficient C1 plus C3 multiplied by x2 squared, and C2, as you see here, it is not shown. We have only two variables, C1 and C3. We do not have a third function. We did not use it. We did not use it. So the data which will be used is prepared as arrays. X1 data, which represents X1. We have only two variables, I said, X1 and X2. So the data of X1 is presented as an array with these 5 elements. And X2 data is also shown as another array with these variables, with these values. And the target data, Y data, is also shown as an array as you see here. In real life, this is just given numbers by me, but in real life, of course, they are taken as a result of experiment work. So what is the basic difference between multiple regression and one variable regression? Is here we have to consider all the independent variables, and this is done by combining them to have a combined effect for both. So here X1 data and X2 data are, as you see here, combined, and they will give here a new variable memory called X data. Normally, X data will be as 2 columns of a 2-dimensional array. If you consider X data, I have printed X data here, and look at it, how it looks like. I didn't run the program yet. Here it is. So it is as you see here, a tuple of 2 arrays. This is the first array, and this is the second array. And the outside brackets show that this is a tuple because we have enclosed them within this tuple. And this is an array, and this is the other array. Not more. Now, we shall give the initial guess for the coefficients which we can expect. I have given 2, C1, C2, C3, 3 coefficients. One of them will be neglected, sure. And now, having the expression of the regression function, and having the initial guess, and having the combined data which represents the features, we can pass this data to the curve fit. So we call the curve fit. The curve fit already is imported, as you see here. We call the curve fit function, pass there the name of our nonlinear function. It is called nonlinear model, as shown here. And here is the combined data of the features, X data. Here is Y data. And P0, which is the initial values of the coefficients. This arrangement yields to regression model, which gives you as the output the values of the coefficients, the optimal values of the coefficients, and a covariance matrix. We are interested now mostly in the coefficients. So if we print the coefficients, we shall get the values which we are looking for. Coefficients here, as you see, we have only two values, C1 and C3. You can have also one of them if you want, and if you do not want to see the other, you can extract one of them. And as shown here, maybe, let me show you. When we print here, we print C1 opt. The coefficients here are generally three coefficients, C1 optimal, C2 optimal, C3 optimal. If we are interested with C1 optimal only, so we print it only and we get its value. If we are interested with all coefficients, so we print all the coefficients directly. So this is what I have done here. I have printed the coefficients at first to get the coefficients of interest. And then I have printed C1 only to have it alone. As you see here, its value. If you compare, of course, this is C1 here and C1 here, they should be exactly the same. Okay, now we have defined the optimal values of the coefficients on the regression function. And if we want to plot the predicted values relative to the original dataset values, so we can plot a scatter plot at first to represent the original value, the function y data as a function of the x1 data. As you see here, we are working with one of the independent variables of the features, not both, because it has the same dimension as y data. If you put here x data, which is the combined effect, it will not print out. It will not draw anything. It will give you an error because they have different sizes, different dimensions. So we scatter plot x1 data with y data. This is the original value, and give it the color of k, which is about black. And now we need to plot the predicted values for the given x data. So x data of 0, which is x1. So I can write here, instead of x data of 0, x1 data, or x data of 0. It is the same. I have put it intentionally so that you can notice that. So the plot now, this is the x-axis variable, and the y, or the predicted values, it is the nonlinear model with the x data. Now this is the combined data, x1 and x2, with the optimal values, C1 optimal, C2 optimal, and C3 optimal. And I gave them the color red. If I plot both, I shall have this curve, which represents the relationship. And as you see, it's really very close and there is no error. The dots, the scatter plot with black dots, and the red line represent the predicted values and the original values, as you see. If we want to plot the other feature also, we can do the same thing. We plot scatter plot of x2 data relative to y data instead of x1, x2 only here. We give it the same color, K. And now we exactly write here the predicted values for x2 now. So here x data, but here x2. And the same coefficients which were found as optimal values of prediction. When we plot it also, we shall have this curve alone. As you see, with multiple regression here, if we want to plot x1 and x2 as input variables and the target as the output variable, here we need to make use of three-dimensional plot where x1 and x2 will represent x and y variables, and the target value will be represented by, as you see, z or third dimension. I shall show you this in the coming lectures, but very often, in order to evaluate and to have an idea about the regression quality and goodness, really we use single plot representing each feature with the target, with the same target, each with the same target, and we can do our conclusions depending on that. Okay, so this is a nonlinear multiple regression. As you see, for you, maybe the most interesting and new thing, you heard that the combined effect of the features x1 and x2, which has to be passed to the curve fit here, x data, which has to be passed to the curve fit function, in addition to the function itself and the target data. Now we shall move to another example where we are going to use the OLS method also for multi but linear regression. Generally, OLS works fine and better for linear regression. So we shall try to analyze how we can do that with multiple variables. So as usual, here you see we have imported the required libraries. Remember, we need stats models API, and we call it SM, stats model SM. We have imported matplotlib in order to be able to plot if we want to have a plot. We used pandas and Numpy as we are working with arrays. Pandas is usually needed when we want to work with data frames, and this is also very often needed, especially when the features are given within a dictionary and we want to construct a data frame from the data. This may be shown in this example or in the following example. In order to get, because we are going to work with arrays and the values are selected randomly, so we at first use numpy random.seed with a value of 42. This guarantees that the randomly selected values will be repeated and will be the same and will not vary with every time when we run the program. The number of values or samples which we are going to use is given as 20. The expression of the features, here we have 3 features, x1, x2, and x3. x1, as you see, as an array, randomly selected values. The number of values is 20. And these values are scaled or multiplied by the value of 10. We have done the same for x2. This is the data of x2. They are selected randomly also and multiplied by 5. And this is also the same thing for x3. Yes. To have an idea about what we are doing, here we have an array practically. So if we print x1, we shall have an array, values of which are multiplied by 10. x1, here is x1, this is the array, as you see, and these values, as you see, more than 1, because normally the random gives you values between 0 and 1. If you multiply it by this value originally without multiplication by 10, it is 0.374, and the other values are the same. But as you see, this is, as you see, a single dimension array, which is resulting from this operation here. We have another array like it here, and here a third array the same. Sometimes you may think what I have got is the data which I have got an array, or it is a list, or it is a tuple, and you are maybe confused. You can use these statements I have included here for you, just to inform you about it, to use the function isInstance function. So, for example, if you use the if condition, if-else statement, if isInstance x1 list, which means if the instant x1 is a list, then print x1 is a Python list. Else, print x1 is not a Python list. But it is indeed here, as we know, according to our practice, it is an array. So we shall have x1 is not a Python list. It is an array. Also, you can write if isInstance x1, if x1 is an P array, so print x1 is a Python array. We will have this written, and it will not be as, or it is not an array, but it is an array, so we'll have an array. So what we will get that x1 is not a Python list, x1 is a Python array. If we look somewhere here, x1 is not a Python list, x1 is a Python array. This is just to be sure about the type of data you are working with. Okay, now we have known x1 and x2 and x3 data values. We want to know the y value and express the regression function by including x1 and x2 and x3 with a given coefficients and added noise. This added noise is randomly added values. It is called epsilon. Here we have generated an array, multiplied it by 1.5, and added this epsilon to y to get the value of y for every x1, x2, and x3. If you want to have an idea about y, I have printed the first 5 elements of y. So y here, as you see, this is y. This is the first element, second, third, fourth, fifth, and so on. So it is also, as you see, an array. Okay, now we have an idea about the target, and we have an idea about the features. I have given you here a short summary, interesting for you, that substates models in Python expects the independent variables to be as two-dimensional array. So all the independent variables must be as a two-dimensional array, and each column of this array, each column will represent one of the features. Okay, so in order to make combining between the features here, in machine learning, yes, we use usually Numpy column stack. It is ideal for combining these features to give at the end a two-dimensional array. We have three variables, x1 and x2 and x3. So what we are expecting to have, we shall have an array with three columns. Let us do it. So now we take, or we have imported NumPy. From NumPy we call column stack function and include there x1 and x2 and x3, and the result will be the array X, which is a combination of the three features. Three columns, each one represents x1, and the second one x2, and the third column x3. If we print it and decide what is the size of x, because we have three columns, so we will have 3 multiplied by 20, which is the number of values for each column. 3 by 20, we will have 60, which will represent the size of this two-dimensional array. Now, if we print it and have a look at the first 7 rows of this two-dimensional array, here it is X, and these are the 3 columns, first column, second column, third column. This represents the values of x1, this is x2, and this is x3. And this is a two-dimensional array. As you see, we have here 1 bracket, 2 brackets, so it is a two-dimensional array with 3 columns. As you remember in the previous work, we used, in order to take in consideration that the intercept value must be displayed and taken with an interest, we have to add constant. So from SM, we add constant of x, and this will be now, this x now is this 3-column two-dimensional array. If we add constant of x here, additional column will be added with values equal to 1. I have shown you this one day. So if you have a look at it, I called it x5. So you will have, this is the first column representing x1, this is x2, this is x3, and this is the column which represents the add sum. So comparing the values here, you will see this value, exactly the same value here. 3.5 will be 3.5, 2, 4, 4, the same, and so on. So now we have already prepared the program to take into account the intercept value. At what is left now? Nothing. We have to call our OLS value, OLS function, ordinary least squares function from SM, stats models, and pass there the target and x5, which is the last two-dimensional array. This will give us a setup, which is the model of regression. Usually, we can write here directly fit function and get the results, or as I have done here, to be clear for you, model dot fit will give you the results. The results, as you remember, will be a table, a comprehensive table with a lot of information about the results of a regression. So if we print results summary, we shall have this table as we have got before, but now we shall have the estimation, prediction of the three variables x1, x2, and x3, and the intercept. So here, these are coefficients, as you see. 5.18 is the intercept value. x1 is the coefficient of x1, coefficient of x2, the coefficient of x3. To judge about the goodness and quality of regression, here we can look at R squared. It is about, as you see, 0.965 from 1. 1 is the optimum, the best result which we can achieve. But here, as you see, it is 0.965, which is really very excellent and means that the regression is carried out without any problems. But also, without looking at the R squared here, we can calculate the R squared here as we did before by using scalar. So I think we should import scalar if necessary. It is necessary now, or maybe it is already here down imported. Yes, from scalar matrix, I have imported the mean square error because considering the R squared already we have that value. We have that value with the OLS. I am sorry. So from the matrix now we have imported the mean squared error. To this function, mean square error, we pass y and the predicted y. Y already we know it. The expression of y already known to us. And what we need is to evaluate the predicted values. We know now the coefficients of intercept and x1 and the coefficient of x2 and x3. I have taken them from the table and included them here. I have got y prediction. And now I pass it with y so that through the scalar, we can have an idea about the mean square error. So I print the mean square error of scalar here, mean square error of scalar. I have printed it to have an idea also about the goodness of our fitting. The value here is about 0.529, which is not bad. Remember, I have told you that the value of the MS mean square error must be very small, as much as possible. Of course, the best case to be 0, but here this value 0.5 is also, according to my practice, is very good and means that the regression process has been carried out very successfully. So now, as you see, we have got directly the coefficients of the three features with the intercept by using or by passing generally the combined x, which represents x1 and x2 and x3. And this was done by, as you remember, by NPy column stacking of these values. Now, if we want to show also the goodness of our regression by drawing here, by making drawing, so I have made a scatter plot for the feature x2 and y, and then I have plotted the x2 with the y predicted value. Y predicted, we know it. It is given here. It is already known to us. So instead of y, I have put here y predict. And now I shall have the original data set dependency, the scatter plot, and the predicted value. And if you look at them as a scatter plot, you will see that in blue, these are the values of the original data set, and in red, you will have the values which are predicted by our program. As you see, the values are very close. This value is very close to this value also close, these are close. Every pair of values of them is really close enough to give you a pictorial judgment about the accuracy of the work. Okay, now we have done multiple linear regression by using the OLS, and we have seen that the result is excellent. We have found the coefficients, and we know now how to combine the values together, and I think this is a good practice for you. Today I want to show you also how I can do the same by using LabVIEW. And I shall try to build the block diagram with the same approach which is done by Python here, and with the same scaling values to be as close as possible to this example, so that I can get very similar results. So I want now to go or to keep Python away and to go to LabVIEW. Here is my program. Let me explain to you the program, and then we will analyze it and see the results. So at first, this is the data set of X1. This is a generator, random number between 0 and 1. This is a for loop. The for loop will execute 20 times, so that to get 20 values, and will be, because the number of samples were 20, as you remember, and I have multiplied the output array by 10 as a scaling factor. So I have generated in this array the values which are generated by X1 in Python. Similarly, I have generated another array multiplied by a scaling factor of 5, and I have generated the third value, the third variable, input x3 multiplied by 2. These 2 and 5 and 10 are the same scaling factor which were used by the Python. Now, I have established here a for loop which will be executed here also for 20 times, and I have inputted to this formula, to this for loop a formula node and created inputs to this formula node. The first one is called x1, exactly as I called it in the Python. Here I call it x2. Here it is called x3. I am not going to change anything with the values, so in the equation of x1 is f1 equal to x1 multiplied by 1. It is the same. f2 is equal to x2. f3 is equal to x3. And the output here will be f1, f2, f3 given here also and created at the output. The regression function here is given as you see here, 5 plus 1.5 multiplied by x1 plus minus 1.2 multiplied by x2 plus 0.5 multiplied by x3. This is the same equation which we used in Python, but without added noise. Now we shall add noise to it. So the output here is y, which represents this equation, and to this y, this is y, go with the line down, I have added this noise, which is generated by using a uniform white noise. I can, of course, generate it differently. I shall try with you just a little bit later. But the amplitude here is given 1. The seed value is taken as 42, as I did with Python. And now this value, this array is added to the array which represents y. So this is y total, which will be used for regression. In LabVIEW for regression, I am using general linear fit.VI. I right-click here, go to the mathematics, go to fitting, and here you will find the general linear fit.VI. This virtual instrument, which I am going to use because it is really general and it is linear, so it's used here now, and I have an input to this is y, so I connected the y value to it here. Now I want to carry out the process of combination of x1 and x2 and x3. I have used a build array here. This is the x3, this is x2, and this is x1 combined together with the array. And number 1 here is added to add constant of s. So at the output here, I get an array, two-dimensional array. You remember, you see two lines, two parallel lines. This is the H array number 4, and this array represents the X5 array which we have seen before. So this array, of course, must be also added to the function here as required. Here is the H function. This weighting function is not required. You can work without it. You can add the weight you decide. And also here, this input will present the tolerance and accuracy you require from the virtual instrument. I have asked this accuracy, which is comparatively very high. And here I have selected the least square method to be used. So all the inputs to the VI are available, and at the output I get the best fit array, which has the values directly calculated here, which represent the best fit values. And let me go back to the block diagram. And here also I have an output of arrays which gives the values of the coefficients. And remember, we have there 4 values. The first value, which is the intercept, and the other value, C1 and C2 and C3. I have written for you in OLS Python, and we have got the intercept 5.18. Here we're having 5.29. Exactly, it is not the same, but it's very close. And this is the value of x1, the coefficient of x1, coefficient C1. This is C2, and this is a value of C3. In order to plot also the scatter plots, I have taken the input. Here is the variable x1. Here is the bundle array. Here is another bundle array. I have bundled the x1 with y, and this will be y. This is y, as you see here, y. But here it is y with added noise. This is x1 with y, and the other bundle x1 with the predicted value. I have made an array of them, and now this array will be displayed, which represents, here, and you see it also in white. We have the original values, and in red we have the predicted scatter values. Look how close each two values are to each other. I think I have also estimated the correctness or the goodness of the function. Yes, I have taken y. Really, I should not take this y. I should take this y with noise, which is much more accurate, and add here the predicted value. Let me see what I have got and then change it. If we go to the front panel, we shall see the R square and the RMS value. The RMS value here is 0.32. Remember, in Python it was 0.5. Here it is 0.3, which means this is more accurate than the OLS algorithm. And the R square, it was there, if you remember, 0.96. Here it is 0.99, which means it is nearer to the value of 1. And again, working with LabVIEW here is more accurate than with the OLS. But what I have remembered, let me try to connect here not this y, but the y with added noise, and see what is there a difference between them? A little bit. Here is the y with the noise. Now if we go back and run the program, here it is closer really. Here it is 518. Now it is 516. The values are closer. I mean the values of Python results and the LabVIEW results are very closer to each other. And concerning the error here, it is 9.8. It is 9.9. It's very high and very, very good. And again, if you remember RMS, it was there 0.5. Now I have got 0.5. So I think it should be like this. Instead of y without noise, I have to include the y with noise, because this is very simple. Why? Because I have used y with noise in the regression process here, and not y without noise. So as you see, the system works perfect, and I hope that I am not in hurry. I am not quickly talking to you. I have explained to you how it works. One more thing here I want to try with you maybe. Here I have included the noise as a uniform white noise and added it to the data. Let us go in LabVIEW and add a normally distributed noise. We go to the mathematics, to the probability and statistics, to the probability here, and here we can with continuous random function. Let us see what it is right for you. It is labeled here, continuous random function. Now, the number of samples will be 100. I will take 100. It is 128. I will write 100. And I will give a mean value equal to 0. The mean constant. I wanted 0. And the standard deviation, I wanted to be about half, which is normally practical values, half. And now the output will be added to Y instead of the output of the uniform noise. Here, I shall take it, as you see, and connect it here. And now let us go back and see the results. Are they much better or worse? Yes, there is some problem here. It doesn't give response here. I have to go here and to define normal distribution. And now when I go back, maybe it will work. Yes. So now here 5.18, now it is 4.49. It is maybe worse than before, not better, but it is working and gives reasonable results. And as you see, the figure also here is very close to the predicted values of the figure are very close to the original values. And concerning the accuracy, here it is about 1.9 as before. So the difference is not that much, but we can work with either of them, with continuous random VI as added noise to the useful signal Y, or we can work with this uniform white noise. It is the same. Okay, so again, making a summary for you, I have generated the data values for X1, the data value for X2, the data values of X3 as arrays, array 1, array 2, and array 3, scaled them by the same factors which were done by Python. Then I have introduced them to the formula node. This is necessary only in order to get the expression of the function, which is Y, in a written mathematical way, which has been done by Python. So it is given the same equation here to get the output of Y. I have added to Y the noise, and I have here made it add sum by adding 1 here, and I have combined the values through the build array to get the H matrix or H array here. At the end, all the values required by the general linear fit are available, and as you see, we have got what we want. Thank you for listening, wishing you the best, and see you in the coming lecture.